So welcome everyone, let's get started. So welcome back. So we're going to talk today, this is going to be the third lecture. So it's again going to be a review of so probability, covering a bunch of so topics. We're probably going to so try and fly through this. So on Thursday we can get to some new stuff that'll be interesting. So again, so this lecture will be so mostly review, but you're so it's always free to ask questions, and a small number of questions while we're doing this is so keeps the lecture so like a little bit more interesting. So let me just review a few things on the web page. So as you should find, the links are updating as we're going. I update them every day after class. The notes from so last week Thursday are now posted. If you click over on the YT, so that'll be the video up on YouTube. What's important today is that so homework 1 is out, right? So if you click this link, it should bring up over here the first homework here is posted. I still have to update so the link on Canvas and everything, but so everything is live. So the homework will be turned in as a PDF. You can create it in like any form you want, and then you can save the files as PDF, right? So I figure you can figure out how to do that. It's much easier for us to grade so with it as a PDF. So yeah, so again, I recommend you try and write so parts of your answer in LaTeX, whether you do the whole thing that way or not. So it's up to you as long as it's clear. There are basically 4 questions on the homework, right? The first 2 you should definitely be able to get started on and do after the lecture today, and actually you should be able to do the 4th one as well. The 4th one, I will ask you to create a plot. So in Python, it does not have to be in Python. I recommend you to do everything like this in the class in Python. Actually, in class today, assuming we finish everything, I'm going to basically show you how to do something very similar. And the exercise, the homework will be to kind of change some aspects of what we're doing, just so just to get familiar with it. So okay, and then the third question will make more sense after the lecture on Thursday. This is not due until Tuesday, September 13th. So you've still plenty of time to work on this. So okay, and so a couple of other things. If you want to contact me about a specific question, I've got my email that you can email me. So that's the preferred way to contact me. You can come talk to me after class or in my office hours time. If you tell me something right after class, I can often give good feedback and stuff then. But I might not remember all the details, right? So if it's something specific, it's better to also send me an email. I will read my email, I'll respond to them. If it's a question about something, like the homework, and it's not something super specific to you, the preferred thing is to post on Canvas. So they're on Canvas. A lot of people probably have similar questions. If you have questions, between myself and the TAs, especially Anna, we expect to answer questions fairly quickly on Canvas. Questions about the homework sent to email, I will not answer as quickly as I will if you post the question to Canvas. Okay, so if you want a faster response, you should post it so to Canvas. If you email me something that should be on Canvas, I may reply after a while saying, hey, you should post this on Canvas, and I will give you an answer. Okay, so that way it's kind of, it prevents us from answering the same question over and over. But there's some specific questions to you, that you need to directly send to me about details of your status or something. Yeah, so those are great with email. So okay. Yeah, and now that the homework is out, you might want to start looking at the office hour times. I saw on the first, so quiz 0, that one will be worth about one quarter as much as any of the other quizzes, but it was going to be similar in length and scope to the other quizzes. I guess the other ones will be about actual kind of the technical material you're going to learn instead of the syllabus, but hopefully it gives you a sense of the sort of things you'll be asked to do on the quizzes. Yeah.
So homework is due 2 weeks from now, and we can post questions through the forum and not through Canvas.
Yeah. So the discussion forum on Canvas. Yes. Yeah. So don't if you send me messages on Canvas, they get forwarded. So to my email, I'll still see them. If you leave like a comment on the grading, I probably won't so see that, right? So so if you prefer to use the Canvas way to message me, that will also go to my email, and that's also fine. But general questions about the homework should go in the discussion board where everyone can, can see them. There can be a discussion about if there's anything that's confusing. Yeah.
Do you have templates we could use for the homework, or should we just?
So yeah, I do have a template posted. Let's see, if you look in, I think maybe it's at the bottom here. Let me see. The thing I did last year, which people found helpful, maybe it's in the syllabus, is that, yeah, so if you go to this link, it's, so the link here that's linked off my webpage, it's gonna have a template of some form. I think it's for an older class I took. One thing I did in the past, I posted the source of the LaTeX for the homework. I wrote the homeworks in LaTeX, right? So you can use that source and then you can write your answers in that. So I'll plan to do that as well. I will post the source through the tab in Canvas that has information about the homework. Yeah. So great. Let's see, anything else? Oh yeah, one more thing that hopefully we will get to in class. There's a link here at the end of the lecture notes that says, so Colab, this is the link to a file that hopefully we'll talk about today, and that will be useful for your, that'll be useful on your homework. You'll see a number of these throughout the semester. So that will always be linked off the main file on the web page if we discuss it in class. So okay, so let's get on to the lecture here, right? And so as I said, there are all these kind of things that end up as like boilerplate in the syllabus that I think are important to go over. So today's part of this is about safety and addressing sexual misconduct as well as other sorts of misconduct. So the university treats this so very seriously. There have been incidents on campus. So in the past where there have been sexual misconduct, this happens on college campuses, unfortunately. I've been with the new administration, I've been pretty happy to see their public-facing responses on this. It seems like they're taking it very seriously. I will take this very seriously. Anything associated with the class. So I will do my best to address it. In most cases, that ends up being reporting. There's information about if you are witness to something about this, or it's affecting you, there's information on the best place to report it. And also on these lines, so if you feel safe at any time, say if you're studying late on campus, so there's a number you can call, and so you can get like a ride someplace if you feel it's dark and you don't feel it's safe. And so there's more information about it here at this link. Okay, so it's important to have a safe atmosphere in the classroom, and so I will do everything that I can to keep a safe atmosphere here, and I hope you feel that way everywhere on campus. So great. So let's get into the discussion of the lecture. I just want to quickly review. We talked about random variables, and one way to think about random variables, and we're going to think about two of these. So we're going to talk a little bit more today about these joint probabilities and conditional and marginal probabilities. There's one way to think about this, which is a probability table, and this works when you have discrete random variables. And so we're going to think about these two random variables. And in this example, you have, and remember, a random variable is mapping some sort of random so the outcome of a random process to a value. And so the first random variable is going to be C, which is representing whether someone has if they have cancer or not. So if it's going to be 1 if they do have cancer, and 0 if they don't have cancer, right? And then there's also going to be a test, right? So we're going to be thinking about people, whether or not they have cancer, if they've had a test. And so T is a random variable, whether the test was positive, right? So positive is supposed to indicate that they do have cancer, and so negative then is going to give value 0. So a lot of these random variables are going to be things that are, so we'll talk about ones that have these numerical values where we take like an average of them. This is often cases for a probability table. It's useful if this is going to be, 0, 1 can correspond with true and false, right? And so then we say that C is true, or the probability of C, that means that C is equal to 1 is going to be like a shorthand for this. All right, so and then you can write these in a table. So C equals 1 versus C equals 0. And you can have, and then you have so that's whether they have cancer or not, and then whether the test says they have cancer or not would be T equals 1 or T equals 0. And tests are not always completely accurate here. Okay, so we want to write down the probability of certain things happening here. And so if someone thinks they need a test and they actually test positive, then you might say the probability that they have cancer and they test positive for cancer might be 0.1. That would mean that's what both are occurring with so probability 0.1. So this would be the probability of C equals 1 and T equals 1. So it's both of these things occurring at the same time. If I just have they test positive but they don't have cancer, so the test is wrong, be 0.02. And if they do have cancer, oh, no. This is they don't have cancer, but the test says that they do have cancer, then that's 0.02. If they do have cancer, but the test says they don't, this may be 0.5. And if they don't have cancer, which is the most likely case, and then the test says that they don't, we might get 0.83. Okay, so what we see as if you remember the rules of probability, this is the total sample space. It's now a discrete sample space here, right? This is the discrete sample space. Each of these values is between 0 and 1, right? And so if I add all of these up, they are disjoint cases. None of these can all be true at the same time. If I add them up, it should total to exactly 1, right? So the probability is 1 that one combination of these events occurred, right? So these are the only cases we're actually so going to consider. And then there are a couple of things we talked about. Let's say conditioned. We want to think now about conditioned on the cancer being true, right? So the probability of something given that the cancer that the person being tested does have cancer, right? We're now conditioning on this case here. Remember the probability, it's the probability of, say, something like the cancer is true. So if this is that the test is 1, given that the cancer is there, so it's probably C equals 1 intersection or comma the test equals 1 conditioned on their that there is cancer there, right? So we're restricting to this probability space, and this is only 0.15 or 15% of the total probability inside this green area here. So we're looking at the intersection and say dividing that by the probability that that we're restricted to, and this is 0.1 over 0.15. If you add these up, and this is so 2/3. So given that someone has cancer, 2/3 of the time they're going to test positive. Okay, so that's tells something about the accuracy of the test, right? And so the higher this ratio, probably the more accurate the test is in this way, right? And so these random variables, are these random variables going to be independent of each other? So how would we check if they were independent of each other? What property could we check? Yep. Right, so you might want to check probability that T equals 1, right? How do we check the probability T equals 1? Well, we would add up these two things. This is called the probability of T equals 1 is so-called the marginal probability, and I'm adding up 0.1 plus 0.02, which is 0.12, so about 12% of the time that the test is positive. So then we would compare the probability the test is positive, 0.12, versus the probability maybe that the test is positive given that they have cancer, which was 2/3. Okay, so is this independent? No, it's not independent because this is not equal 0.66, right? So these are not independent. So would the test be good if the test was independent? No, it would not be good. It would not tell us anything useful, right? So a test for cancer, a test for COVID, if it's independent of whether you actually have that thing you're testing for, you do not want it to be independent, right? So you don't always want your random variables to be independent of each other. Most of the rest of the class will actually want our random variables to be actually independent of each other. So, okay. So great. So this is kind of this encapsulates a lot of the right thinking. If you kind of understand this, you should probably get most of what you need for discrete, so random variables and events. We'll talk about expectation in a bit too. That'll also be important. But for continuous random variables, right, the case is a little bit more complicated. I can't write down the discrete possible outcomes inside of a table if I have continuous random variables. So I want to next talk about continuous random variables. And to do that, I need to talk about density functions. Okay. And so to talk about density function, I'll be with respect to a random variable, I'll use x. And I'm going to write the density function f of x. Okay. So, and this will be from the sample space, a function, and typically this just be, so the outcome will just be the real value scalars. Okay, in some cases we'll want to think about this as vector value outcomes, but we're not going to worry about that right now. Okay, so for right now we'll think about this as a function. Remember, this is the so the sample space. Okay, this is the space of all possible things. This can be a continuous space now, not just the discrete space, right? Like test equals 0 or test equals 1. We now have a continuous possible space. It could be something like height or the amount of rainfall or like the temperature. And so then it's going to have a real possible value of the outcome here. And this is kind of like the notion of the probability, but it's not going to quite be a probability with continuous random variables. So this is trickier for two ways. One, we can't write it as a table, so it's hard to think about in discrete terms. So we're going to need a more complicated mathematics just to describe it. And second, the language is even harder to talk about this. This is going to be a density function. I'd like to say probability here, but the probability of getting exactly 0.56 inches of rain is going to be 0. So like a measure 0 is what they say. And so it's not actually a probability here. It's going to be instead, we'll often call this a likelihood. Okay, so we'll talk about the likelihood instead. And that's something like a probability, but we won't, but it will, for technical reasons, we'll see again a little bit more about this. We won't be able to call it as a probability. Okay, but this will be the probability, so density, so function, and we'll commonly just written as PDF, right? So this is not the portable document format, as you have to turn your homeworks in. Don't turn your homework in as a as a probability density function, but so this probability density function will just refer to it as a PDF, and okay, so and then I want to talk about the probability of these things. I need to put some rules on what the PDF can take And to do that, it's actually easier to talk about another function, uppercase f of x. So it's same random variable, I'll use uppercase f of x. And this will be again from the sample space, but now we'll go from 0 to 1. Okay, and this is going to be called the cumulative so density function, and typically just called the CDF. And this is defined in terms of the integral. So I can now define this at some value. Let's say, what do I use in the book? Let's say, so like a mega, and this will make sense if, so most cases we'll talk about where this is also the real numbers, then I can, it's simpler. You can, it doesn't need to be the real numbers, but I'm thinking about an outcome of the sample space, okay? And this is defined as the integral from this equals negative infinity up to, let me write W down here. Let's say integral of, yeah, let's just try and match the notation in the book. So the outcome from W equals up to T of f of x of, so W, so D, so W here. Okay, so I'm integrating the probability density function up to a certain value, right? So I'm going to think about that the sample space is going to be the real numbers, okay? And I'm going to have a probability density function, okay? This would be f of x, okay? So it's going to have some value under here, and I want to evaluate this, okay, up to a point T, okay? And so I'm going to look at I'm going to try and look at the integral up to this point T here, okay? And so this is going to give me kind of a function which is okay, so this function here now is going to be uppercase f of x, and it's going to go from 0 to 1. Okay, so I'll plot another example which is slightly better than this, but the integral up to this point is going to be the height of this blue curve here. Let me just finish what I'm saying. So the height of the blue curve will be all the integral up to that point. So this is always increasing. This can't decrease. All right, question.
The character inside the capital.
So the character inside here, so that's a T. Yeah. Thanks. Great. Thanks for asking. So yeah, so let me show you, yeah, let me jump to Collab, which you can get from the link off the web page here. All right, so this is so Collab is a cloud service from Google. It has Python installed. You don't need to install Python. You can type stuff in here. This is on my account. But you can copy this onto your drive if you click there on the copy to drive, and then you can edit it on your own. I can click in here and edit it. I need to do basically two things. So in Python, there's the reason we prefer Python in this class and a lot of data sciences. There's a lot of libraries which are super useful, and it makes it easy to kind of perform a lot of the tasks we'll be doing with the short amount of code, because a lot of the techniques where things we're working with are already built in and implemented. And so we're going to look at these libraries. The first one is so matplotlib, which is a plotting library, which will allow me to create a plot like this. Okay, and then I'm going to use a kind of a package that has some statistical functions in it, and I'm going to import the normal function. The normal distribution will be the most useful distribution. We'll talk about it a fair bit in this class, especially the next few weeks. And then I'm going to import NumPy, which is the kind of the package which allows me to to talk about vectors, right? Naturally, variables as vectors. It makes it very transparent. So to work with this, if you've ever worked with MATLAB is a much older programming language that was built just to work with vectors and matrices. It's not quite as natural as MATLAB, but it's quite good, as we'll see throughout the semester. We're only going to use this to store the data we're going to plot in, and then a math library because I need to do I think it's like because I have to take a square root. Okay. Okay, and you have to load those all in. Okay, the first time you do it, it's going to take like 20, 30 seconds to load them in, but I did it before class. And then I'm going to run this simple piece of code here, set the mean equals 0, variance equal 1. I'm going to plot what's called a normal distribution, which is this blue curve, which kind of like the curve I drew on the slides. This is the probability density function of a normal distribution. And it has a mean and a variance. We'll kind of give more intuition to what that says. And I've set the mean to be 0, and the variance to be 1 here. And then I've also applied the cumulative density function, and that is the integral of the normal distribution up to a certain point, right? So this is always increasing. It goes from 0 to 1. Okay, and I can easily change this right in the browser. Let's see, it's a little bit more finicky on the iPad. Oh. Okay. Okay, if I change this to 1, and you have to do shift return, compiles it, or I can hit that little square there. What happened is I replotted it, and it's now shifted the middle of it, the mean, to 1 here, right? It just redoes it right here. I can actually drag this out of here, right? So I can drag this, I can copy it, and you're going to plot something like this and then paste it into whatever your format is you're turning your homework. Yeah.
Changing variance from 2 would widen it, wouldn't it? Or
yep. Yeah. So the variance, okay, we'll do. Okay, let me do that, and then you could see it replot in real time. Let's see. Come on, plot. And good. Okay, it should be wider than it was before. All right. Okay. And I plotted it. Okay, there are ways to put this. So I've called this normal function with the x minus mean sigma. I've put those all in there. There are other ways of doing this. There's a lot of information on the web. You're allowed to look up what functions mean on the web in this class to do the programming. Don't worry about that. That's how everyone does it. So I expect you to do this. I'll give you example stuff, and you'll need to modify them in the homework and such, and expect you to look on the web to figure out how to play around and figure out how to modify these things. Okay, a lot of you are either computer science majors or if not very adjacent to computer science. I figure you should be able to figure this stuff out from some very limited examples. As you'll see, almost everything we do for programming in this class will be, okay, as a method to learn the underlying material. Okay, any more questions on this?
I have a question on the previous one. I can just ask you later.
Sure, okay, great. So I want to get back to the lecture. I want to finish all the probabilities, core probability stuff, so we can get into kind of starting to do some estimation on Thursday. Okay. Okay, the next important thing that we need is the expected, value. This is one of the most useful tools to come out of probability. We're going to be estimating things, and we're trying to say we're going to get expected values of things that we're going to compare to the true thing that's unknown versus some sample estimate of it. And so the expected value will be kind of one of the core things we're talking about in this course. Okay, and so the reason we need to talk about random variables is because you often talk about the expected value of if you have a random variable x, the expected value of a random variable x, right? So that's what expected. That's one of the reasons we have random variables, so we can talk about expected value in a way which is we can write down mathematically, and then we're going to analyze processes and algorithms by looking at the expected value of these random processes and algorithms. So kind of this is a super important thing to understand. Okay, we're going to have elements of the sample space. So if we have a discrete random variable, then it's going to be the written as the sum over all the possible outcomes of the value of that outcome times the probability that is the outcome that the random variable takes. Okay. Okay, and I'll write this down for continuous random variables, and then we'll go through some examples. With continuous random variables, it's gonna, again, we need to use this probability density function instead. Oh, I have one more thing I wanted to say. Yeah, after I have, let me see, I missed this. We need, the property we need to have about this probability density function is that the integral over everything in the sample space of f of x, sorry, this should be, yeah, w of x dx, this has to equal to exactly 1. All right, this is the key thing. It's like a probability, and it integrates to 1, but I can't evaluate at a single point. I can talk about, so I can say for n, an event A, which is a subset of the sample space, I can say that the probability of an certain event is equal to, or x is in this event, is the integral of the w of this omega in A of let's see, of x. Okay, so I talk about the probability of an event here, but I can't talk about the probability of a specific sample outcome. I can talk about probability of events, so I need to use integrals here. And that's similar to what's, maybe I flipped that off too quickly, but I can integrate continuous random variables to get probabilities, because I can't just count stuff. I have to integrate over a continuous space, like height, like someone's height is between, what would be a normal number of inches, between 60 and 72 inches. I can look at that probability, but I can't say their height is exactly 67.84 inches. That doesn't really make sense because it's not actually discrete values. Okay, yeah.
So what's the difference between omega A and A is the event?
A is a subset of the sample space. Yeah. So A here, right? A might correspond with a region here, right? So it's a subset of the sample space. It's not a single spot. That would be omega. It would be a single point. And the A is a subset and has to be like a measurable subset of the sample space.
So just like with the age sample, it's 60, 78, the probability of that.
That's in that range, right? It doesn't have to be a continuous range. It can be discontinuous, two pieces, two different ranges or something, but I have to be something I can can integrate over.
And it tells us the probability of that.
Of something falls in that range, right? An event is a subset, a measurable subset, and a sample outcome is a single thing, right? With discrete things, we have a finite set of discrete things, but with continuous, we have an infinite number of discrete things, right? Or an infinite number of things, we have to think about whole sets of them, right? And so to define an expected value, I have to, now I'm just replacing the sum with an integral here. Right, so it's, it's basically the same thing. I don't have the probability anymore, so I have the probability density of this random variable. So I'm just integrating over the value times its likelihood. Okay, so it's, so it's the likelihood, it's kind of like a probability, but it's, I can't talk about the probability of a specific omega, but I can integrate over it. And so that's all I need to do here. And in this course and in most of data analysis, we'll only do this for things where this calculation is actually going to be pretty easy. If you run into something where it's not easy, then usually you decide to model it in a different way so it is. So, okay, before we get to an example, well, how about we start with one example for first? Okay, so let's start with the discrete x, which is equal to a die, a six-sided die. So the outcome is 1, 2, 3, 4, 5, 6, right? And let's say they're all equally likely. Each one, I have that the probability of xi equals 3, or any of the other values will be exactly 1/6. Okay, so then I want to say the expected value of the die, right? What's the expected value of x here? It's going to be the sum over kind of omega in say 1 up to 6, right? Of the value of omega times the probability that x is equal to omega, right? And this is going to be equal to the sum, I guess, omega of w times 1/6. It's 1/6 for all of these things. Okay, so 1/6 times sum over over 1 plus 2 plus up to plus 6. All right, and so this is equal to 1/6, and that's going to be 21. So it's going to be 21 over 6 is going to be 3.5. Okay, so the expected value of a die, if I roll one die, is going to be 3.5. Okay, right. So pretty standard expected value.
If the probability of each die is different.
Yep. Then instead of factoring out the 1/6 here like I did, I have to write out these things, right? It's 1 times the probability of 1 plus 2 times the probability of 2. And if you have an unfair die, you have to deal with that.
Okay.
Yep. Okay. I'll go through. Usually with a continuous random variable, we're just going to be like given the expected value. For instance, like for like a normal distribution, we're going to be given the definition of the normal distribution will be by the mean and the variance, like I had written before, and the mean is going to be the expected value, right? So we're just going to be kind of given that in most cases.
We'll go over any numerical analysis class.
No, we're going to do, later we're going to do a little bit numerical analysis when we get into, like, we're going to compute the principal component analysis relates to eigenanalysis, and we're going to have to compute these things. We're going to come up with a simple algorithm that's going to converge very quickly, and you'll see a little bit about that, but it's not as full-blown as you see in kind of your linear algebra class probabilities, or especially computational linear algebra class. Yeah. So we'll see a little bit, but not till like the second half of the semester. Okay, so you won't need to worry about that. Now, for probability, the goal is not to make things hard. The goal is to make things easy. Okay, so I don't want to get into any complicated calculations in the probability. My goal is to avoid those things. Okay, if you're setting up in data analysis, one of the cool things is that you can choose how you model something to a fairly large extent. It's not like you're given a calculation you have to compute somehow, and then you're figuring out the best way to do that. You're co-designing the calculations and the modeling so that the calculations are easy, right? So if I run into something so that the calculations are really hard to compute, it's probably a bad model, in fact. And that's true for two reasons. One, it makes the computation hard, and I don't like hard computations. And two, if the computation is unstable, means if I am off by a little bit, I get a very different answer. That's probably a really bad model, because I want it to be stable with respect to noise and variation in the sensing of the data. So if I come up with a formulation that is hard to compute numerically, I've probably done something wrong. And we'll talk about maybe a little bit towards the end of the semester some ways that you can, forgive if we cover this or not, but ways that you can slightly tweak the model so that it becomes numerically more stable and the calculations become easy. Okay, so it's an interesting question, but it's something that you really, in this course, the reason to know numerical analysis is so you can avoid it. Okay, that's why all this math is useful. Sometimes it's knowing where not to go, right? And so that's what a lot of this class is kind of. That's where we'll use a lot of the math. Yeah.
So what does that expected value of 3.5 actually context, for example,
Right. Oh, okay. So I mean, one way is, let's say I go to a casino and someone says, you put down $4, and I will give you $1 for every number that comes up on the dice. So if I roll a 6, you get $6. If I roll a 2, you get $2. And then you can say, well, the expected value is $3.50. So that's a bad deal. I'm not going to do it. That's what it's kind of the expected. If I put a dollar sign in front of the numbers, then that kind of tells you how much the outcome is, right? I could put a different dollar sign depending on the numbers. Maybe the 6 is actually only worth $10, and all the other ones are the numbers. I can redo the calculation and then see if it's worth it for $4. Okay, and so this expected value, it can be the expected amount of money, it could be something else, right? Points on an exam or something like that. This is a way to quantify the expected outcome where there's probability involved. It simplifies the probability down to a single number, and that's a lot easier to work with than some more complicated distribution. All right, so that's kind of the expected value is kind of the single number that tries to summarize all of the randomness together. Okay, one of the other, the expected value is great to work with. One of the reasons is the linearity of expectation. Okay, this is a super important property. Let's say I have two random variables, x and y. Okay, and I look at the expected value of x plus y. I can write this as the expected value of x plus the expected value of y. Okay, I can decompose this, and so this will be important because I may be able to calculate or be given the expected value of x and y individually, and so then I can, and if I am trying to have random variables where I add them together, let's say I roll a dice and then I flip a coin, and each of them, there's a joint proposition that I'm going to get some money from both the die and the coin, but you have to do both together. Well, I can look at the expected value of both of them and add them together individually. I don't need to somehow work through all the combinations of these things. Yes. This is true in general. Yeah, this is super powerful. Yeah. Yeah. Okay, the other thing you can do is if I have a scalar a fixed scalar value alpha, okay, and I look at the expected value, and let's say alpha could be like 10 or something, right? Or I'm putting units on something, it's dollars or cents. I can say alpha of x is equal to alpha times the expected value of x, right? So I can also factor out these combinations. So linearity of expectation means I can decompose it by addition and factor out scalar quantities. I can't in general do, it's not in general true that the expected value of x times y is equal to the expected value of x times the expected value of y. This is in general not true. Okay, so I can't in general do that. Not, okay, good. Important, so I almost missed that. This is not true in general, so I can't decompose by products, but by addition I can. Okay, and so often a common mistake in doing some derivations, trying to understand probability, is to do this. So this is something you want to avoid, making sure you do that. Okay, let's go through another, so how are we doing? Let's go through another example here, where, okay, let's say that the height I measure of say a basketball player was a combination of their true height h plus the height of the shoes, right? So if you look at basketball players at so like at the combine or something, they were measuring their height in game. Some basketball players wear shoes that give them more lift, right? If you want to be really tall and you're standing on stilts, you're going to be a lot taller. Now you can't run around too well on stilts, but they do put height in the shoes, so that the height might be the true height might be kind of a continuous random variable, but the shoe might be a discrete random variable. So I can write this as a table. So as the height and we'll write everything in inches here. So let's say the height is between of a shoe that a basketball player might wear is between 1 and 4 inches. Can't quite imagine playing at a 4-inch platform, but I guess it's I think 3 inches is not that unreasonable. Maybe 3 is still pretty large, but in the case of this example, we'll use this, and we have a probability table. Let's say there are 4 types of shoes, and they give you a lift of 1, 2, 3, or 4 inches. But we'll say that but let's say I know that the expected height, that the true height, that means if I'm standing kind of without shoes on, I'm going to say it's a normal distribution with the mean of 1.755. No, let's not actually, let's not do inches. Okay, no wonder this example is weird. This is in, so this one's going to be measured in, so centimeters instead. Actually, it should go up here. So this is in centimeters, and this will be in meters. Okay, and there's some sort of variance. I'm not going to need the variance here. Let's say 0.1 meters. Okay, so this, and I know that the expected value of the height is going to be exactly 1.755 in meters. So I want to figure out what the expected value of the height wearing shoes is now. Yeah.
Just to clarify, is that a variance? Is that saying?
That's looks like it's a standard deviation. Standard deviation, great. So I'm not going to need that. Okay, but that's the standard deviation. Yeah. So I can write down, I want to know the height plus shoes. So I'm going to write this as the expected value of the true height plus the expected value of the height wearing shoes. Okay, and so I know what this is, and so I can decompose it using linearity of expectation. But the height wearing shoes is in centimeters. So I want to write this into meters. So what I actually want to do, so what I actually need to do is to divide this by 100. Because I need 100 centimeters in order to get, in order to get the answer in meters. So I can write this as expected value of S divided by, so divided by 100. Yeah, good. So, or maybe I write it in meters. So then, no, the outcome, I'll want to get this in meters.
Multiply the meters by 1, right? The expected height is actual.
Yeah, okay. Yeah, I can multiply the meters by 100. I get the result in centimeters. If I want the result in meters, I would divide. Yeah, I'd multiply this. No, I divide the centimeters by 100, right?
Yeah, sorry.
Yeah, I think the book has it probably the other way. But that's okay. This will work. You'll see a slightly different example. Okay, so we'll get the height in meters now, expected height in meters, and now I take the expected value of this, and this guy is going to be, and the 1/100 is factored out either way, so this is not going to be involved in the core computation here. And now I need to do 0.1 times 1 plus 0.1 times 2 plus 0.5 times 3 plus 0.3 times 4. And the outcome of this is it's going to be 3 as it turns out. Okay, so the expected height of the shoe is 3 going to be 3 centimeters. So this is going to be 1.755 meters plus 1/100 times 3. So centimeters here. Okay, and the outcome is 1.785 meters, right? Because I divide the 3 by 100, it goes into the second spot of the decimal. Okay, so this is how I calculate the expected value. I've mixed together a continuous and a discrete random variable. I can decompose the costs. I can factor out the change of the units. Change of units is a really useful thing to think about when I'm changing the factoring stuff out. That factors out of expectation in some nice way here. Okay. Okay, good. This makes sense? Yeah, all right. Okay, all right. Okay, the next thing we want to talk about is the variance. Okay, so if I have expectation, that's the single most kind of simplest representation of a probability distribution. The variance is kind of the next thing. If I were to give in one number, I'll give you the expectation. If I give you the two numbers, I'll give you the variance in addition to the expectation. Okay, and the variance is kind of talking about how spread out a distribution is. We saw this with that plot of the normal distribution. Okay, and it's written as for a random variable x, and this is written in terms of the expectation. It's how spread out it is with respect to the expectation. So if I write the variance of x, this is going to be equal to and it's a squared notion. So this is a little bit strange when you see it at first. The expected value of x minus the expected value squared. Okay, so this is kind of odd, saying, okay, what's the squared deviation from the mean? All right, so I've got, it's fun to draw pictures of continuous things because you can kind of see them pretty well. The mean, this would be the expected value of X, and I want to know kind of the average squared deviation from this mean, or the kind of the expected value of how far I am from the mean squared.
Yeah, so in the parentheses is the expected value of X, right?
Yeah, that's great. Yeah, expected value of X. Let me make sure that's clear. X. Yes. Okay. Now, what's important to note here is that this expected value of X, this is a constant. Basically, this is defined based on the random variable X, but this, so I can kind of calculate that first, whereas this one is the expectation I need to kind of calculate for the variance. Need to calc for the var X. So it's expectation over the squared deviation, and I'll kind of assume that I know the expected value of X in here. And there's another common form of this, and this is equivalent, is I can write down the expected value of X squared minus the expected value of X quantity squared. Okay, again, these are not the same, right? Because I can't factor out the product X times X. That would, if then they were the same, this would always be 0. That would be uninteresting. And you can derive one of these from the other. If I take that expectation out, actually this is pretty useful to do. Let's say expectation of X minus the expected value of X quantity squared. What do? I have to factor this out. I kind of expand the squared polynomial inside of here, right? So I get an X squared, I get plus the expectation of X squared, right? And then I get minus 2 times X times the expected value of X. Okay, so this, I've just expanded out the square inside of here, right? Now I can push this X, now I've got sums and minus signs, which is, I can push through the expected value into different parts. Okay, I get the expected value of X squared. Okay, that's the first term. What's the expected value of this? Well, this was a fixed constant. The expected value of X is a fixed constant. So actually, and I square that fixed constant. So the expectation doesn't do anything on that. That's a constant, right? So I just get out the expected value of X kind of squared again. Okay. And now I have the two factors through, and I get the, and in fact, this second expected value over here, right? This guy right here, this also factors through. That's also a constant. So that's being brought out as a coefficient. Okay, and then what's remaining is this guy, and that gets pushed through the expected value on X. Okay. And so now I have these, now this term is equal to this term, but I'm subtracting 2 of them, right? So I get this, the first one comes down, this is the same as before, and now I do subtract, I add 1 of these and I subtract 2 of them, and so what I get is minus 1 of these guys squared, right? Okay, so I've derived the second form. And notice how I can't factor out the X squared, but I can factor out the expected value, which is seen as a constant within this formula. Okay, so expected deviation from the mean, I can see this in a couple of ways here. Okay. Okay, Okay, so the variance is kind of spread out. There's this other notion, the standard deviation, okay, of random variable x. So I say the variance of x, I usually write it this way, whereas the standard deviation, you know, I typically write this as sigma of x. This is just the standard way of writing this. And this is equal to the square root of the variance of x. Okay, so why do I talk about the standard deviation? The variance is this nice form where it's written as an expectation. And this is kind of the quantity we use. This is actually pretty nice to work with and calculate with and write bounds with. The standard deviation has the advantage that it's the same units as x, or the expected value of x, right? So if this is over kind of meters, the standard deviation is in the units of meters, whereas the variance is in the units of squared meters, which is weird to think about in the context of height. Okay, thinking about squared meters is kind of weird. So I take the square root and then I'm thinking about the meters again. So it's easier to think about the standard deviation. In fact, if I draw a picture where I write the mean, I'll typically draw the standard deviation as kind of the average, something like the average variance, the average deviation. It's actually the square root of the average squared deviation, but it's something I can draw. Its units align with those of the mean, so I can kind of draw it in this picture. I can't draw variance, or maybe it'd be like a cube or something weird like that. But standard deviation makes sense to draw. Variance does not really make sense to draw. Okay. How are we doing? Oh gosh, we are, okay. Okay, good. Okay, let me try and, I've got, okay, 15 minutes, I'll be okay. All right, so let me just say this, the covariance, we're gonna start talking about pairs of random variables, and the covariance is how they vary with each other, which is going to be just the expected value of x minus the expected value of x times y minus the expected value of y. Okay, I'll just define this now. We might talk about it a little bit later, but it's how these two variables vary with each other. So they can vary with each other at the same time. That means they're kind of correlated. If one grows bigger, the other grows smaller with respect to their own means, then they're anti-correlated with each other. We'll maybe bring this up again, just so I've defined it. It's up here, but it's not going to be super important, at least in this class. But later on in data science, you'll find lots of uses for that. Okay, so the last thing I kind of wanted to do today was going to be is the notion of joint distributions defined for continuous random variables, right? So we started this lecture today with the probability tables. So the probability tables on these discrete random variables, and you could write them down in a big table, and everything added up to 1, and it was nice. And so conditional, so distributions. Okay, but I want to do the same thing we did with probability tables for discrete random variables, do that with continuous random variables. And this is, again, mathematically going to be a little harder to write down the definitions and to say, because I can't say probability in a lot of places. But these will be kind of important for modeling our data and our kind of and the models, the models which fit the data. Okay, once you're used to these, they're very natural to think about, but to define them, it's going to be a little bit sort of trickier here. So again, we're going to be talking about two random variables, X and Y, and now they're not going to be kind of independent with each other, and we want to capture these notions of how they're not independent with each other, but they're going to be these continuous random variables. Right, so we're going to write down the PDF, and we'll write this as f of x comma y, right? And this is going to be from a sample space of x cross a sample space of y. So it's going to be a bivariate function. It's going to take in two sample outcomes of x and of y, and it's going to output to a real value, technically between 0 and up to infinity, not including infinity. So at least for discrete, I guess, yeah, we'll say not including infinity. There's some mechanisms you can make that work, but beyond this course. Okay. Okay. So what this looks like is I have of x, f of x comma y, and I'll take in two possible sample outcomes, and I'll write these as lowercase x. These are uppercase and lowercase x and y. I'll try and write the size a little bit different. It's clear if you write it like in the textbook, so I'll try and stick with this, and hopefully the size will be different enough you can tell this. But this will be kind of, you can think of this. So at least in the discrete case, this is kind of like the probability that x is equal to x, that the random variable x takes on the value x, and that the random variable y takes on the value y, okay? But if this is continuous, actually the probability of this, of a particular outcome, like it rained exactly so many inches today and the max temperature reached a certain value, those would be two possible outcomes. But the probability of hitting that exactly on the head with all the precision, infinite precision, is 0, right? So I can't really write down the probability. But I can think about this probability density function, which I could integrate over. Yeah.
Why is the sample space 0?
This is the sample space I map to, which is the outcome, the value space. Think of this as real values. And I'm going to integrate, and it's going to act like a probability, right? You're asking why it's not between 0 and 1? Not negative, because I have to have, one of the properties of a probability density function has to be greater or equal than 0 for everything. Think of a probability has to be greater than 0, and it has to integrate to 1. Okay, yeah, this is a great question. Yeah.
Wasn't your original slide on PDFs omega to R instead of omega to 0?
Yeah, I should have written to between 0 and infinity there. Yeah, sometimes it is R, happens to be a particular important subset of that.
I was wondering just for
No, that's a great question. The original one should have also been restricted. It was always, the value is always greater or equal than 0. Yeah.
I can't really do that's why.
Yeah, so those are the sample. This is, so the first one is, so this is the sample space of x, so that's the omega. Yeah, okay. This is like a think. This is not really an equality here for continuous things. I'm trying to write, this is the way to think about it, but it's not an actual equality. Don't write an equality down. I've written something kind of like, so I don't have a good mathematical notation for this, but yeah, it's analogous to, we're going to get a notation in the next couple of lectures that will allow us to write something kind of like this, so something that it's proportional to, but I'm not going to introduce that yet. So I'm just kind of writing, it's kind of like this. So think of it like a probability, but don't write it that way. Okay, yeah.
Why is it?
Yeah, okay, because the value could be smaller than 1, but in a very narrow range. So if I integrate it, it still doesn't exceed 1. So if I go back, yeah, so if I go back to my collab example, actually, let's say I make this variable 0.1. Okay, good. Let's run this. What happens? The variance got really, oh, I didn't do this right. Yeah, I'm not applying this the right way. Okay.
Shouldn't the plot be divided by variance, not by sigma?
No, you want to divide by sigma, otherwise you change. But I should divide by sigma here, actually. Actually, what do I? Let's try this. Yeah, so what's going to happen here, I think this is right. I'll have to double check this. But the integral should stay 1. So if you look, the height is now higher here. I've integrated over a much smaller region, right? As makes this smaller, the integral of that PDF should 0, 1. Right, so if okay, now if I made that variance even smaller, the integral of this still has to be 1, but because it's very narrow or more concentrated, the height has to be much higher there. So as long as it integrates to 1, I'm still okay. But the height can be much larger, and it can be up to and approaching infinity. Yeah. Great. Okay. Back here. Okay. All right. So how do we deal with these things? Yeah, so I have that the integral over x in, I have to do a like a double integral of f of x, y, dx, or I guess would be dy dx, this has to be equal to 1. So the integral has to be 1. So if it's very concentrated, the values have to be very high, so it integrates to exactly 1. That's why it goes up to infinity, but it's always greater than 0. Yeah.
What if we graph like dimensional?
Yes, in fact, there is, probably won't, yeah, there's a picture of it in the book coming next, but I don't have a plot of this today. We will plot 2-dimensional stuff later in the semester. You should take the visualization for data science course, and you'll learn about ways of thinking about high-dimensional data and how to visualize them. There are ways of doing it, but it's beyond a lot of the simple things that we'll do in this course. Yeah, it's a great question. We'll think about them through linear algebra, and I will tell you when your 1- or 2-dimensional intuition kind of holds and when it doesn't, because I've kind of thought through all these things. Okay, so this integral is 1. Okay, let's see. We'll probably, I think I'm going to, yeah, I'll probably stop here, and we'll probably do the rest of this in the lecture on Thursday, and hopefully we're not going to get too far behind. Yeah.
You have like a distribution for rain.
The y-axis has to be what?
Does it have like what does it mean?
Yeah. So it can it's the likelihood. So it doesn't. It does not have units. Yeah.
For the discrete structure people,
so for here, for t equals 1, why did I not?
For C equals 1, why didn't you just add 0.1 and 0.05?
Oh, so that's the probability that someone has cancer. And I did do this down here in the denominator. I have calculated probability 0.15.
Okay.
Summing these two
So
things.
that's the probability of them having cancer and testing positive.
That's just the probability of them having cancer. That's 0.0. That's 0.15 is the probability of having cancer. Right? And I'm ignoring the test and what's called marginalizing over the test. If I marginalize over the value of the test, I just want to know the probability that of.
So is 0.66 the probability of having cancer and testing it or not?
That's the probability of testing positive given that I have cancer.
Okay.
Typically, you'd write this the other way. I think the book does it the other way. The probability of having cancer given I tested positive on the test.
And why is it not?
That's more intuitive.
Why is it not combined other than it's a discrete table anyways?
So I've broken it down. I have more information here. And if I wanted to kind of restrict my, but if I wanted to ask these questions, like the conditional probability or the marginal probability, I can read that off the table. But if I collapse it all together, I might not be able to recover other questions.
Okay.
So certain joint probabilities. Here, I'm gonna stop the streaming on YouTube a second, and then